All right, so the last topic in Chapter 6 is to focus on some general properties of conductors in electrostatics. So first, let me highlight two facts about conductors. First off, in electrostatics, the electric field is always zero inside a conductor. And the second thing, if a conductor is charged, the excess charge resides on the outer surface. So this first figure that I've got shown here, this highlights the first bullet point. That the electric field inside a conductor is zero. So I've got a positive charge over here on the left that induces a negative charge on the left-hand side of the sphere and a positive charge on the right-hand side. And over here on the left portion of the figure, we see why that means that the electric field is zero inside. And so I've got, at a point P, I've got three electric field vectors to add up if I want to talk about the net electric field inside the conductor. I have the electric field due to the positive point charge, so that's EQ. I have the electric field due to the negative portion of the sphere due to the polarization, that's EA. And then I have the contribution from the positive portion of the sphere, that's EB. And if I add up all of those vectors, EQ, EA, EB, inside that conductor, at any location, those three vectors add up to zero. And so the electric field inside a conductor is zero. This bottom figure highlights the second bullet point. I've got a positive point charge that's been placed within a cavity of a conductor. And what that does, without touching, what that does is it polarizes the neutral conductor. So negative charge collects on the inner surface, and positive charge accumulates on the outer surface. Again, the net charge on the conductor before I make contact is zero. Once I make contact, the positive point charge essentially is transferred to the conductor, and the net charge on the conductor is positive, and that charge is immediately residing on the outer surface. And this picture over here on the left kind of gives you some sense of how that's possible, right? Because the charge has already redistributed, and then once you make contact, essentially you're just left with that positive charge. Okay, the last thing we want to talk about, the electric field at the surface of a conductor. So I've got the magnitude of the electric field expression. I've got that highlighted already. The electric field at the surface of a conductor is proportional to the surface charge density, sigma, and then divided by epsilon naught. So if the surface isn't charged, then there's no electric field at the surface. The electric field is also perpendicular to the surface. So that means in the positive or negative n hat direction. So depending on whether the field is coming out or going into the surface. So if you look at the surface here, this one's a little curved, and so that means in this region the electric field is pointing that way, over here, this way. And so if your surface is curved, that means the electric field is pointing in different directions at the surface, right, at different locations. This bottom figure just touches on what we talked about on the previous page, that the charge the excess charge for a conducting surface, for a conductor, resides on the outer surface, and the electric field on the inside of a conductor is always 0. So on the left side, I've got a cavity that's filled with a positive point charge, and you see the excess charge resides on the outer surface, and around the cavity inside there's an induced negative charge. So what that means is that inside the cavity, or inside the conductor, outside the cavity, the electric field is actually 0, because if you draw a Gaussian surface in here that includes the cavity, you include both the positive point charge and the induced negative charge, and that total amount of charge is 0 enclosed. And so the electric field inside the conductor is 0. The electric field outside would not be 0, because now the total charge enclosed is plus Q. And then over here on the right, you've got a positive test charge outside of the conductor. So that means there's an induced charge on the conducting surface, negative on the right, positive on the left. But the electric field inside the conductor is still 0. And that's obvious because there's no charge whatsoever inside the conductor.